Wednesday, we are going to have a quiz. So just make it sure that everybody attends that class. On Wednesday, we are going to have a quiz. So let's start today's lecture. What I was telling you previously that flow control, congestion control, and error control or are hinged with the acknowledgement mechanism. And con error control was nothing but it was to detect the error using simple mechanism of checksum. And if checksum is not matching, then you are not going to acknowledge that. Meanwhile, what will happen? There would be a timeout at the sender's end. Now, the problem here is how to choose the timeout value, how to set up this retransmission timer. Now, if you choose timeout value to be very small, then obviously there would be unnecessary retransmissions. If you choose timeout value to be large, then there it would be long waiting time before packet can be retransmitted. So in both the cases, problems may occur. Now the challenge here is that delays in the network are not fixed. So at one particular time that retransmission or RTT is different. At another particular time, the RTT may be different from the previous time. So what is needed? Your retransmission timer must be adaptive to the current network condition. And that is what is the challenge, and we'll devote one whole lecture, 2 hours on this particular topic, that how to actually calculate the retransmission timer. This is one of the most important topic of the transport layer, especially in the context of TCP. Now, the next slide is going to be most important, and I wish that everybody should pay attention on that. And please be very careful while I'm discussing this particular thing. So what this slide is saying that what are the acknowledgement dynamics, and this is given in RFC 1122 and RFC 2581. What are the different acknowledgement dynamics? And here we'll discuss most important point that is known as delayed acknowledgement. So what is happening if you read the first statement, that this is the event which is occurring at the receiver. If a in order segment with expected sequence number arrives and all data up to expected sequence number is already acknowledged. So what it is saying that suppose you are waiting for packet number 23 and this packet number 23 arrived and all the data packets means 22, 21, 20, all these are already acknowledged. Then what is the action? So this is the event that expected packet with expected sequence number arrived. All the data previously prior to this expected sequence number which has arrived is already acknowledged. Then what would the action of receiver? Then action is receiver may wait for 500 millisecond for next segment. If for 500 millisecond there is no next segment, then acknowledgement can be. So receiver will kind of delay the acknowledgement for 500 millisecond in anticipation that in this 500 millisecond maybe 24 can also come, and then we can send the cumulative acknowledgement. So what is the first event? Packet arriving with expected sequence number. All data up to that expected sequence number is already acknowledged. Then what receiver will do will delay the acknowledgement for 500 millisecond. Actually, 500 millisecond is a standard, you can say, time, but you can tweak with the implementation by writing some commands, and you can, reduce this 500 millisecond also, reduce or increase, whatever. So you can delay the acknowledgement, receiver can delay the acknowledgement for 500 millisecond. If within that 500 millisecond no new segment comes, then acknowledgement will be sent. Now, if arrival of in order segment with expected sequence number comes, but one another segment has acknowledgement pending, means this case that 23 आया, उसके पहले का सब acknowledge हो चुका था, it will delay, 24 भी आया, now 24 has come. Now if 24 has come, now the second case would be there, that arrival of in order segment with expected sequence number, arrival of in order segment with expected sequence number, one other segment has acknowledgement pending. This 24 has arrived, 23 is waiting because you have delayed the acknowledgement. Then you are not required to delay. You send, so maybe after 100 millisecond, 24 comes, so 23 is already waiting. Then you are not required to, delay more. You immediately send the cumulative acknowledgement for both of these packets. Immediately send single cumulative acknowledgement acknowledging both in order segment. Now what I am asking, you read these two event and associated actions and tell me in totality what is going to happen. My question is how many packet actually you can cumulatively acknowledge. If these two event and associated actions are true and these are standards, then how many packets actually you can acknowledge in a cumulative manner? Just think over it for 2 minutes and tell me if this is the situation. Yes, anybody?
Sir, two.
Who is speaking? Means
Sandeep.
only two packets. It's not more than that. And that is also true because the way conditions are set up, you can, if everything is happening fine, if everything is okay, so every second packet actually you have to acknowledge. So first of all, that particular thought that, okay, you can cumulatively acknowledge many packets, that is not there. Every second packet you have to acknowledge if things are happening fine. Now the third event, arrival of out of order segment higher than expected sequence number. Now this is the event. You are waiting for, suppose you are waiting for, you are waiting for, you are waiting for packet number 16 and instead packet number 20 arrived. So there is a gap. Now, if this is the happening, means this is out of order. Out of order. Waiting for packet number 16. Up to 15 might have been acknowledged. You have acknowledged up to 15. waiting for packet number 16, but 20 arrived out of order. Then what you need to do, immediately send duplicate acknowledgement. Immediately send duplicate acknowledgement. And what is the duplicate? What is going to duplicate acknowledgement? You have now in TCP, what is the acknowledgement mechanism? Just wait, just suppose I have sent packet number 1, I got, and this is correctly received. What would the acknowledgement number? Suppose I got packet number 10, sequence number is 10. So what is the acknowledgement number if it is correctly received? Suppose this is sender and this is receiver. What is the acknowledgement number? Yes, Sandeep?
So next one, 11.
11. So you send packet number 11. The acknowledgement number would be ACK 12. So in TCP, the acknowledgement number always tells that what is the next expected packet. Now suppose you are waiting for packet number 12 and packet number 12 got lost or delayed or whatever. But you have sent packet number 13 also. You have sent packet number 13 also. 13 received correctly. So this is out of order. In this case, you are not required to wait. You will immediately send a duplicate acknowledgement. Which acknowledgement should I send now here?
So 12.
ACK 12, which you have already sent for packet number 11. Now this is the important part here. You send that duplicate acknowledgement and you may buffer the packet also. Packet number 13 will be buffered. It's not deleted. So this is different from GBN. GBN was discarding the packet. Here you will buffer that packet. Now the next is arrival of a segment that partially or completely fills the gap. Suppose after sending duplicate acknowledgement, packet number 12 say comes up. What is there? 11 is there, 12 is there, and 13 is buffered. So what you will send? ACK. What is the acknowledgement number? Yes, anybody? 13 arrived out of order. You send the duplicate acknowledgement. After some time, and you buffered the 13. After some time, 12 also arrived. 12 also arrived. So what was the acknowledgement number here?
14.
So 14.
14. You will send the 14. So that's the fourth case. Arrival of a segment that partially or completely fills the gap. Immediately send the acknowledgement provided that segment starts at the lower end of the gap. So let me take one more example. Suppose you have sent packet number 20, it received correctly, you send 21. Suppose you send 22, 23, 24, all got delayed or lost for some time. And then you have sent packet number 25, 25 has been received. Suppose 25 has been received. So what's the problem here? 25 is out of order. You will send what acknowledgement? You will send acknowledgement number 21. You send ACK 21. Duplicate acknowledgement. After some time, suppose 24 is received. After some time, 24 is received. What will you send when 24 is received?
21.
ACK 21 again. Now suppose after some time 22 is received. Or sorry, after some time 21 is received. What will you send?
22.
Then you will send 22. I think you understood the thing. ACK 22. So miss, you need to see that it is filling. If it is filling the lower end of the gap, then you need to adjust your acknowledgement accordingly. But in these three cases, if one everything is fine but one other is already pending, then immediately send the acknowledgement. You are not required to delay the acknowledgement. If out of order is coming, immediately send a duplicate acknowledgement. If arrival of any segment which partially or completely fills the gap, immediately send acknowledgement provided a segment starts at the lower end of the gap. So this is how the acknowledgement dynamics work. Now suppose let's take one more case. Take one more case, or rather a question. Can we cumulatively, after seeing all these cases, can we cumulatively acknowledge more than two packets, two segments or packets? In this particular scenario, after seeing all these four cases, can we cumulatively acknowledge more than two packets anytime? Yes, anybody? Tanmay? Karimullah?
No, sir.
You're saying no. So let's take one case. Let's take one case. Suppose you have sent 20 and you received it correctly, you send ACK 21. Now you have sent 21, 22, 23, 24, 25, all these packets. Now you have transferred all these packets. Now what has happened? Suppose 25 received first. What will you do? बोले यार ठीक है आ गया, send me 21, ACK 21. So afterwards 24 got received. Again send ACK 21. 23 was received. Again send ACK 21. 22 received. You send ACK 21. Not 21 is received. Now suppose 21 is received correctly. So what acknowledgement will you send? ACK Karimullah.
So 26.
26. So here you have acknowledged, no? Cumulatively many packets. Yes or no?
Yes, sir.
So now what is the actual takeaway from this slide is that if everything is happening fine, not more than two packets can be cumulatively acknowledged. Yeah, in case of out of order errors, there may be a situation where you can, like in this particular situation, you have acknowledged 1, 2, 1, 2, 3, 4, 5 packet in cumulative manner. But if everything is fine, packets are arriving in order, not more than two packets can be cumulatively acknowledged. So this is what is the acknowledgement dynamics of TCP, and many people get confused in this, and in books also it is not written in a proper manner. Now, if there is any question, you can ask. Otherwise, we can move ahead. Any questions? Any doubts? Think over it. Think about the situations. Okay, there are no question, we can move ahead. Our next topic is TCP congestion control. And as I told you that initially this particular uh, responsibility was of network layer. But after 1986, after the congestion collapse, the responsibility was shifted at the ends at the TCP layer or transport layer. So it's a very simple mechanism, and mechanism is implemented at the sender. Like flow control mechanism is kind of controlled by the receiver. And congestion control is like sender is trying to tune according to the implicit feedback given from the network. Their receiver was tuning according to its buffer space. In flow control, what was happening? Receiver was tuning the sender according to the buffer space remaining at the receiver. Here, network is giving implicit feedback. It's not explicit. There's a difference between implicit feedback of congestion and explicit feedback of congestion, and we'll see that later on. So here, what is happening? Network is kind of giving sender a implicit feedback, and sender is accordingly controlling its sending rate. So sending rate is controlled by two parameters. One, sending rate is controlled by the receiver using advertised uh, window, and then sending rate is controlled by the network using a congestion window. So the actual situation is there are two windows, two variables. One is flow control window, which is set up by or advertised by the receiver, and other is the congestion window, which is adjusted based on the feedback in bracket implicit from the network. So what is the actual send window? Actual send window is going to be the minimum of flow control window and congestion window. That's what you need to understand. Now, if you go for TCP standard implementation today, they follow RFC 2581. And this reference document specifies 4 standard congestion control mechanisms that are now in common use, and every operating system implements them. And these 4 algorithms are slow start, congestion avoidance, fast retransmit, and fast recovery. So before moving or jumping into the details of congestion control, just try to understand that the major notion behind devising these type of technique is that they have understood that in wired networks, lack of acknowledgement is very rarely due to the bit errors or errors in the packet during the journey. during hop-to-hop data transfer or packet transfer, it is very rare that some bit errors are going to occur. So what is happening majority of the time, maybe 99% of the time, if there is a lack of acknowledgement, it is due to some congested router. And I told you the routing queue management and queuing time, queuing delay and all that. We have already discussed this. So majority of the time, most of the time, what is happening, if you're not getting acknowledgement back, there can be two reasons. Either the acknowledgement is dropped on the way back because some router was congested and queue was filled, or the packet itself is dropped by a router because queue is full. So if you are not getting acknowledgement back, that's an implicit feedback that network is getting congested. That was the, you can say, the heuristic, and which was proven true also later on behind the congestion control mechanism. That if there is a lack of acknowledgement within time, it means that some of the packet is dropped by router on the path. And with this particular premises, we'll try to understand the TCP congestion control algorithms. Congestion control is governed by two variables. One is congestion window, CWND, another is slow start threshold value, whose initial value is set up to power 16 minus 1. Congestion control works in two modes. One is slow start and other is the congestion avoidance. Slow start up to the point of SS thresh, that if your CWND is less than SS thresh, then you are in slow start mode. If your CWND is greater than or equal to SS thresh, then you are in congestion avoidance mode. Now please be very attentive while you are understanding this, and if you are facing any problem, you can always interrupt me. How it begins? Initial value of congestion window is set to 1. And for every acknowledgement which is received by the sender, the congestion window is increased by 1 segment. Now, the name is slow start because you are starting from slowly, but it's not that slow. In fact, if you see it carefully, the increase of CWND is exponential. You can see here that suppose you have, so just for a while, if we say that we are going to acknowledge each and every packet, so I have sent packet number 1. Right now CWND is 1. I have sent 1 packet, suppose packet number 10. Send, we receive the acknowledgement ACK 11. As soon as I receive the acknowledgement, my CWND would be CWND previous plus 1 acknowledgement we have received plus 1. So next CWND would be 2. So what we'll do, we'll send 2 packets, 11 and 12. Suppose we receive these 2 acknowledgement. So in CWND would be CWND plus 1. So the CWND was 2 when you receive the first acknowledgement. So it would be 2 plus 1. When you receive the second acknowledgement, तो यहाँ पे CWND 3 हो जाएगी, और जब ये भी मिलेगा तो ये CWND 4 हो जाएगी. And it's not like this is happening in discrete manner. As and when you receive the acknowledgement, you increase your CWND variable by 1. Now suppose you are having delayed acknowledgement, so you have sent suppose 20 packets. You have sent say 20 packets, 20 segments of packets, and your current CWND is 20, and you have sent 20 packets. You may receive 10 acknowledgement. So after receiving all the 10 acknowledgement, your CWND would be 30, because for every acknowledgement you will be incrementing your CWND by 1. So as a matter of fact, it is near exponential. Your rate of increase of congestion window is near exponential, because suppose the case is there, आपने एक भेजा, next time दो हो जाएगी, दो भेजे, next time चार हो जाएगा, चार पैकेट भेजे, next time 8 हो जाएगा, 8 पैकेट भेजे, next time 16 हो जाएगा. So considering that every packet is getting acknowledged, if some packets are getting acknowledgement, then you are not, it's not strictly exponential, but it is increasing at a rapid rate. Now this will go like, suppose if I see this, so we have sent one packet, we received one acknowledgement, we have sent two packet, we received two acknowledgement. So CWND become 4. Now there's a small question for you guys. Let's see if you can answer it or not. So our CWND was 4 here, but we have sent only 3 packets. Why? Anybody? Yes, Karimullah? Karimullah, are there?
No idea, sir.
Because you are not paying attention. Actually, I told you in the first slide, the send window would be minimum of flow control window and congestion window. So it might be that your congestion window is 4. It may so happen that your flow control window is 3 only. So whatever is the minimum you are going to send. Are you getting my point?
Yes, sir.
So you have to be very careful while the send window is always going to be minimum of congestion window and flow control window. Anyway. Now when your CWND reaches the slow start threshold, means CWND is greater than or equal to SS thresh, then each time an ACK is received, the CWND would be incremented in this manner. CWND equal to CWND plus 1 upon CWND. Each time when you receive acknowledgement, 1 upon CWND would be incremented. So you can see that, suppose I say that at any given time, suppose your SS thresh is 16. So you have sent 1, it was 1, then it became 2, then it became 4, then it became 8. As soon as it becomes 16, it is equal to SS thresh. CWND equal to SS thresh. Now if you send 16 packets and you receive 16 acknowledgement, so next window would be what? 16 plus, for every acknowledgement 1 upon 16, you receive 16 such acknowledgement. So it would be 16 plus 1 means 17. So you can see that it is up to slow start, up to SS thresh, slow start threshold, it is increasing rapidly, means exponentially. But after slow start threshold, it is increasing linearly. Suppose instead of 16, you received 8 acknowledgement due to the cumulative acknowledgement. So it would be 16 plus 1 upon 16 into 8 means 16 plus half. So it will remain 16. If you receive each and every acknowledgement after SS thresh, it will be incremented by 1. Otherwise, it will remain 16. So this is known as congestion avoidance phase after SS thresh. Now, if you see the complete picture and suppose assuming that SS thresh is 8 and every packet is getting acknowledged, we started with one window, 1 CWND1, then it became 2, it became 4, and then it became 8. And after you send 8 packets and receive 8 acknowledgement, next time it will become 9. So you can see from 1 to 2 to 4 to 8, and after thresh, SS thresh, because this is SS thresh 8, it is increasing linearly. So these are the two algorithms, slow start and congestion avoidance. Now, what are the responses to congestion? TCP assumes there is a congestion if it detects a packet loss. So how TCP sender can detect a packet loss? As I told you, because TCP has an assumption if there is a lack of acknowledgement, it assumes, TCP assumes, it's a triggered setup that if there is a lack of acknowledgement or there is a receipt of duplicate acknowledgement. In both of these cases, if lack of acknowledgement up till the timeout means timeout of retransmission timer, or there is a receipt of duplicate acknowledgement. So TCP can assume that there is a packet loss. Now, TCP interprets timeout as a binary congestion signal. अगर timeout हो गया, डुप्लीकेट पैकेट, डुप्लीकेट एक्नॉलेजमेंट मिलने से कुछ शक तो हुआ कि यार हो सकता है पैकेट लॉस हो गया हो, बट अभी पूरा कंफर्मेशन नहीं है. But if timeout happens, TCP can assume that packet has been lost and it is lost due to congestion. And if that is the case, you reset your CWND to 1, scratch. You start again from the scratch, back to square one. And not only that, for next round, you will reduce or half the SS thresh also. In anticipation, यार SS thresh ज़्यादा था, इसीलिए यार पैकेट लॉस हो गया, रेट ज़्यादा थी, नेक्स्ट टाइम फिर से शुरू करते हैं 1 से, स्लो स्टार्ट फिर से शुरू करते हैं, और इस बार कंजेशन अवॉइडेंस जल्दी करेंगे, SS thresh को भी हाफ कर दिया. That is a response to congestion. So if you see the summary total, initially CWND is equal to 1, SS thresh is equal to advertised window size or to the power 16 minus 1. For every new acknowledgement which is received, if CWND is less than SS thresh, then increment the window by 1 for every acknowledgement. Otherwise, if it is greater than or equal to SS thresh, then increment the congestion window by 1 upon CWND on the receipt of every new acknowledgement. If there is a timeout, then multiplicative decrease. Reduce SS thresh to the half of the value, current value, and make CWND 1 again. Any questions from anybody at this point? Tanmay, Divyanshu, any questions?
No, sir.
Correct?
No,
सब समझ में आ रहा है? Anyway. So now the third algorithm which is there in the implementation is the fast retransmit. Now this is interesting. अगर 3 और more duplicate acknowledgement मिल गए, पैकेट गया आउट ऑफ ऑर्डर, फिर दूसरा आउट ऑफ ऑर्डर गया, तीसरा आउट ऑफ ऑर्डर गया, और तीनों के लिए डुप्लीकेट एक्नॉलेजमेंट मिल गया. If 3 or more duplicate acknowledgement are received, तो TCP बिलीव कर लेता है कि यार पैकेट कहीं भटक नहीं रहा है, it is actually lost. Then TCP will perform retransmission of what seems to be the missing segment. हर बार तुमको पैकेट मिल रहा है 25, 26, 27, 28, 24 नहीं मिला, तो 25 मिला तो क्या करोगे? ACK third 23, again ACK 23, again. So suppose this is the situation. Let me draw that. Suppose you received packet number 23, you send ACK 24. So you have sent packet number 24, but it is actually lost. And because your congestion window was there, your send window is bigger, you send 25, you send 26, you send 27. So for 25, you will send ACK. What ACK?
24.
24. For 26 also ACK 24. For 27 also ACK 24. Means kind of 3 RTT हो गई, लेकिन हर बार duplicate मिल रहा है. It means packet is really lost. Packet is really lost. That is the assumption. That is the assumption on which TCP works. Now in that case, what TCP will do will retransmit the packet, and it will not wait for timeout to happen. That's why it is known as not wait for timeout to happen. It will not wait, and that's why it is known as fast retransmit. So you are not waiting for timeout to happen. You are, as soon as you get 3 or more duplicate acknowledgement, you retransmit packet number 24. Because हर बार कहा जा रहा है 24 भेजो 24 भेजो 24 भेजो, 3 बार ये हो गया, you retransmit, you fast retransmit packet number 24. बाकी सब वही होगा. Without waiting for timeout to happen, that particular packet will be retransmitted, but you will enter slow start because packet indeed is lost, making SS thresh CWND by 2 and CWND as 1. Any questions? Okay. अच्छा एक बात बताओ बच्चे लोग, ये डुप्लीकेट क्यों मिल रहा है एक्नॉलेजमेंट बार बार सेंडर को?
24 लॉस्ट हो गया पैकेट.
नहीं ये तो ठीक है 24 लास्ट हो गया, लेकिन बाकी पैकेट पहुंच रहे हैं ना, ये भी तो एक कंक्लूजन है.
बट रिसीवर एंड में होता है जो एंटिसिपेटेड पैकेट होता है, हम उसको वो करते हैं इन ऑर्डर में.
ना थोड़ा सा ऊपर उठ के देखो. डुप्लीकेट एक्नॉलेजमेंट तभी मिल पाएगा जब कुछ पैकेट पहुंच रहे होंगे.
ओह
नहीं समझे?
ना, समझ गए.
कंडीशन इतनी खराब नहीं है, ठीक है, ये कहने का मतलब है. इंजीनियरिंग पॉइंट ऑफ व्यू से सोचो यार, लॉस हुआ कुछ, मान गया बात मान गए, बट इतना भी कंडीशन खराब नहीं, क्योंकि यार लगातार डुप्लीकेट मिल रहे हैं, नहीं बाकी पैकेट तो रिसीव हो रहे हैं तभी डुप्लीकेट मिल रहा है. क्यों? ऑब्वियस है, डुप्लीकेट तो तभी मिलेगा जब उसके आगे के पैकेट रिसीव हो रहे होंगे वहां पे करेक्टली. नो?
यस सर.
यानी कि कुछ थोड़ी देर के लिए हलचल हुआ था. हाँ, इट्स नॉट ए बिग प्रॉब्लम, बट what you are doing, you are taking a knee jerk action. ना फिर से शुरू कर दो CWND इक्वल टू 1 SS थ्रेश CWND by 2. So एक और amendment आया बाद में, which is now implemented. As I told you, all these 4 algorithms are implemented in TCP. It's known as fast recovery. Fast recovery avoids slow start after fast retransmit. What is the intuition? Duplicate acknowledgements actually are indicator that data is getting through. So what you are going to do, you retransmit the packet after third duplicate acknowledgement, retransmit the packet which is presumed lost. SS thresh को half कर देंगे क्योंकि loss तो हुआ ही है. But CWND would be CWND by 2 plus 3. और अगर ज्यादा डुप्लीकेट आएंगे तो उसको बढ़ाते ही रहेंगे। कब तक? जब तक कि कोई क्यूमुलेटिव एक्नॉलेजमेंट ना मिल जाए, मतलब ये जो लॉस पैकेट तुम भेजोगे, जब वहां वो पहुंच जाएगा तो एक नया डेटा एक्नॉलेज करते हुए क्यूमुलेटिव एक्नॉलेजमेंट मिल जाएगा, तब तक हम CWND को ऐसे इंक्रीमेंट करेंगे। फॉर एवरी न्यू एक्नॉलेजमेंट we'll be incrementing CWND like this instead of making CWND 1 again. And when acknowledgement arrives that acknowledges new data, then you will make CWND equal to SS thresh. Fine. जो भी SS thresh उस समय सेट हुआ था, अपनी CWND को उसके बराबर कर लेंगे, और फिर जैसे SS thresh के बराबर हो जाएगा CWND, you will be entering into the congestion avoidance in any case. So this is the kind of fast recovery. हमको जाना है कंजेशन अवॉइडेंस में, बट व्हाई टू एंटर इनटू स्लो स्टार्ट अननेसेसरली? फाइन. सो सिचुएशन इज बैड, बट इट्स नॉट बैड दैट बैड दैट यू हैव टू टेक ए नी जक एक्शन. दैट इज द फास्ट रिकवरी थिंग. फाइन. नाउ depending upon these four algorithms which was included in RFC 2581, different TCP variants or implementations came, and names are interesting. So the first implementation, as I have shown you in the evolution slide of TCP, the TCP Tahoe was implemented, which was having slow start, congestion avoidance, and faster transmit, only 3 algorithms. Then TCP Reno came, which was Tahoe to tha, fast recovery bhi tha. Then new Reno came, which was like a little bit modified fast recovery. And finally SAC came, selective acknowledgement, which is Reno plus selective acknowledgement. Little bit of SR type plus Reno. So if you see Tahoe, 3 algorithm implement हो रहे हैं: slow start, congestion avoidance, and fast retransmit. So on new acknowledgement, एक से बढ़ाएंगे CWND. अगर SS thresh से ज्यादा हो जाएगा तो 1/CWND से बढ़ाएंगे. On timeout, retransmit all acknowledged. SS thresh would be CWND by 2, CWND equal to 1. On third duplicate acknowledgement, retransmit the packet which you have presumed lost. You make CWND 1 and SS thresh CWND by 2. Take an eject action. Then on new acknowledgement, same as the way. Timeout, same as the way. If third duplicate acknowledgement, then retransmit first unacknowledged. SS thresh equal to CWND by 2 and CWND equal to CWND plus by 2 plus 3. In Reno, if subsequent duplicate acknowledgement comes, you keep on incrementing CWND plus 1. जब आखिरी में cumulative मिला, जब वो retransmit वाला पहुंच गया तो cumulative मिलेगा. Then you make CWND equal to SS thresh and enter into congestion avoidance. So you can see here, SS thresh suppose is this, 8 था तो 8 की जगह क्या हो गया, 6 हुआ. 6 क्यों हुआ? क्योंकि CWND 12 पे लॉस हुआ था, तो 12 पे लॉस हुआ तो नेक्स्ट SS thresh become 6. If you see here, Tahoe goes back to 1 and start from there, and Reno goes to what? It was CWND 12 by 2, 6, and then for every subsequent duplicate acknowledgement you keep on incrementing the CWND until unless you get the new acknowledgement which acknowledges new data. So this is what are these 4 variants, 3 variants. Fine. And The last variant is TCP with selective acknowledgement. And here we will utilize the TCP header options. It is based on RFC 2018, TCP selective acknowledgement options, standard track. Good for when multiple packets are lost from one window of data. It can give sender a complete view that कितना queued है receiver पे और कितना flight में है. Selectively you can acknowledge block of data. It uses two TCP options. पहला SAC permitted, may be sent in a send segment for negotiation. भाई हम SAC वाले हैं, तुम हो क्या? And SAC option itself may be sent over an established connection. SAC option ही बताएगा कि कौन से ब्लॉक का डेटा पहुंच गया है, कौन सा ब्लॉक नहीं है. So let's take example and try to understand this. SAC permitted option, kind 2, length 4. SAC option itself, kind 5, length can be variable depending on how many blocks are there. If कई टुकड़े हैं तो लेंथ ज्यादा बढ़ जाएगी, अगर एक ही दो टुकड़े हैं तो लेंथ कम हो जाएगी. कई ब्लॉक हैं, कई ब्लॉक्स हैं जिनके बीच में गैप है तो लेंथ हो जाएगी ज्यादा, इसलिए लेंथ वेरिएबल रखी है. और SAC option, SAC permitted option, kind 2, length 4. For every TCP option there is a kind जो बताता है कि ऑप्शन है किस चीज का, और फिर लेंथ कि उस ऑप्शन में कितना वर्ड आपको इंक्लूड करना है. Anyway, now see with example. Suppose this is the situation. Assume that left edge and is at 500 and transmitter or sender sends a burst of 8 segments each containing 500 data bytes. So start from 500 to 45499, next segment, and next segment. And suppose 5, 6, 7, 8 segments are all lost. So here क्या होगा? Here एक ही ब्लॉक है, एक cumulative acknowledgement भेजने से काम चल जाएगा with no SAC option. The data receiver will return a normal TCP acknowledgement segment acknowledging क्या कि यार 7000 बाइट भेजो अब, ठीक है, 7000 वाला भेजो और कोई SAC ऑप्शन यूज करने का जरूरत नहीं है. तो वी कैन सेंड ACK 7000 here क्योंकि ये चार सब सही मिल गए बाइट नंबर तक. Now suppose the first segment is lost, लेकिन बाकी 7 पहुंच गए. वही पहला एग्जाम्पल ही ले रहा है. ये एक पहला केस था कि आखिरी के 4 नहीं पहुंचे, तब क्या होगा? सपोज पहला वाला नहीं पहुंचा और बाकी 7 पहुंच गए, सब आउट ऑफ ऑर्डर पहुंचे. अब देखिए वहां पे क्या हुआ. अब सैक ऑप्शन यूज होगा. कैसे यूज होगा? एक्नॉलेजमेंट 5000 इस पैकेट के लिए, क्योंकि 5000 नहीं मिला. इस वेटिंग फॉर एक्सपेक्टेड सीक्वेंस नंबर इज 5000 नहीं मिला. लेफ्ट एज कहां पे है? 55 पे आ गई. राइट एज कहां पे? 6000 पे. पहला पैकेट जब मिला तो हम एक्नॉलेजमेंट नंबर हमने 5000 भेजा, लेफ्ट एज बताया यार 5500 से 6000 तक का है मेरे पास. फिर दूसरा पैकेट मिल गया, एक्नॉलेजमेंट नंबर अभी भी 5000, बट अब देखो ब्लॉक का साइज बढ़ गया. 5500 पे लेफ्ट एज है, राइट एज 65 पे आ गई. इसी तरह इफ यू कीप ऑन सीइंग इट, you can see now when you receive the last packet, यार एसी के 5000 भेजो. 5000 पैकेट से we are waiting. Fine, we are expecting that particular sequence number, but right now left edge is at 550 and right edge is at 9000. So in this way you can tell sender कि कौन सा पैकेट लॉस्ट. इन नॉर्मल सिनेरियो क्या होता है? जितना ही पैकेट मिलता है उसको सेंडर को कभी पता ही नहीं चल पाता है कि पहला लॉस हुआ, फिर हर बार वो भेजेगा. send 5,000, send 5,000, send 5,000, send 5,000. Now let's make this case, starting from here, let's make this case a more interesting. Suppose this is the situation. The second, fourth, sixth and eighth segments are dropped. तो जब पहला पैकेट मिला, सैक को यूज करने का कोई जरूरत नहीं है, एक ही ब्लॉक है वहां पे. सैक इज नॉट यूज्ड, यू जस्ट सेंड एक्नॉलेजमेंट 5500. दूसरा लॉस हो गया. जब तीसरा मिला तो अब यहाँ दो ब्लॉक हो गए, एक 5000 से 5500 और दूसरा 6000 से 6500. So what you are doing when you send packet number B, तो 5000 से 5500 तो आप एक्नॉलेज कर चुके हो 55000. So what you will say, acknowledging when you receive 6000 to 6499, you will still send a duplicate acknowledgement 5500 because you are waiting for 5500, but now you have a block there starting from 6000 to 6500. एक ब्लॉक वहां तैयार हो गया. फिर क्या हुआ, चौथा छूट गया और पांचवा मिल गया. Again you will send, see देखिए, you will send acknowledgement 5500, but now there are two blocks. One block is 6000 to 6500, other block 7000 to 7500. Now suppose you receive 6th is lost and you receive 7th. So then again ACK 5500, but now there are three blocks. 6000 से 6500, 7000 से 7500, 8000 से 8500. So in this way sender would be able to know कि कितना पहुंच गया है और कितना लॉस है. Suppose at this particular point of time, continuing from the previous example, चौथा पैकेट received out of order, चौथा आ गया. सपोज चौथा अगर आएगा तो क्या हो जाएगा, एक ब्लॉक पहला वाला, देखिए क्या क्या होगा. अब कितना ब्लॉक बचा, चौथा पैकेट आया तो कितना हो गया सही, पहला आ गया था, दूसरा अभी नहीं आया है, तीसरा आ गया था, चौथा भी अब आ गया, तो ब्लॉक हो गया 6000 से लेके 8500. 6000 से, सॉरी, रिसीवर रिप्लाइज विद द फॉलोइंग. तो 6000 से 7500 एक ब्लॉक और दूसरा ब्लॉक है 8000 से 8500. As soon as you receive the fourth packet, you have 6000 to 7500 and second block is from 8000 to 8500. That's what is the same. And ACK will be 5500 क्योंकि पहला तो मिला ही नहीं. Now suppose second segment is received. यहाँ पे चौथा मिल गया था और सेकंड भी मिल गया, तो पहला दूसरा तीसरा मिल ही चुका था, चौथा मिल गया, पांचवा मिल गया था, ये सब आ गए. तो अब ACK क्या जाएगा, यहाँ तक सब आ गया 7500. ठीक है, ACK 7500. अभी ब्लॉक कितना है यहाँ पे, अब एक ही ब्लॉक बचा 8000 to 8500. Now if you see the blocks, first block received report most recently received segment, and subsequent block will repeat most recent previous blocks. So in this way you can tell the sender that how many packets are received correctly in a selective manner. So these are about TCP variants. So we have covered a lot of ground today, the congestion control, the TCP variants, and you may revisit this lecture during your spare time. You can watch this video again, and if there is any trouble we can always discuss it again. So in the quiz, or the quiz can be subjective or objective, depends upon the situation. On Wednesday we'll be having one quiz. We'll be having class also, and after the class we'll be having a quiz. And up till today, whatever we have covered will be there in the quiz. there any question, then okay. Otherwise, we can split.
Excuse me, sir.
Yeah.
सर उसमें डाउट था, मतलब जो कंट्रोल्स के एल्गोरिथम्स पढ़े थे ना, उसमें फास्ट रिकवरी